So, dear students, yesterday we have completed up to sampling. In the steps of pesticide residue analysis, we discussed about experimentation. Experimentation is not a usual step in pesticide residue analysis. Usually, the first step is sampling, and the next part of sampling, though it's not the step. Once you complete the sampling, the next process what you should do is transportation of samples, and our intention is to transport the samples as quickly as possible, that is within 24 hours of sampling, because the pesticide starts degrading with each and every passing hour. So if you are delaying the analysis, the result also can vary. So it should be analyzed as quickly as possible. The samples should be transported in a clean, inert container, and that container should prevent any chance of leakage, damage, or contamination. So it should be a perfect container, and that container should protect the sample from any damage, and it should any chance of contamination and any chance of leakage. And one thing we should ensure that the sample should be properly sealed and labeled. That labeling is extremely critical. The sample, the container should be labeled properly, it should be sealed properly, and transported to the sample. Once we if the lab is having heavy load of samples to be analyzed, or somehow our one of the instrument is down and we can't analyze it now itself, then we should keep the samples, store the samples at minus 10 degrees Celsius, so that the degradation of pesticides is arrested. So the sample should be sealed in a container properly. It should be properly labeled, and the container should prevent any chance of contamination, damage, and leakage, and should be transported as quickly as possible and analyzed as quickly as possible. And if we are unable to analyze it quickly, we can store it at minus 10 degrees Celsius. Coming to the next step, after experimentation, sampling, then next step is extraction. So experimentation, sampling, extraction, cleanup, analysis, and interpretation of data. So this is the step by which we go. So the next step is extraction. As the name indicates, extraction means the ways we adopt to extract the pesticides in a sample. The some pesticides are easily, especially the surface residues and all, are easily extractable, but there are certain residues which are bound residues. These bound residues also should be extracted with the procedures which we adopt. So whatever be the steps or procedures adopted to isolate pesticide from sample is called as extraction. And the first thing what we will do is the sample will be brought to lab. In the lab we will cut it into pieces. Just a minute. Hello. Sorry. Sorry. ഒരു ഫോട്ടോ വിടുക, ഞാനൊന്ന് നോക്കിയിട്ട് രാത്രി പറയാം. ഇല്ലില്ല, മനസ്സിലായി, എനിക്ക് മനസ്സിലായി, ഞാൻ നോക്കിയിട്ട് പറയാം. So once the vegetables or fruits are brought to I told we are not permitted to subsample it or cut it in the field itself. Once the sample is reached here, we will chop it and we will crush it in a blender. A normal mixer grinder is used for crushing, and from that crushed sample we use solvents to extract the pesticides. So the crushed samples are used for extraction. So whatever be the extraction method which we adopt, the extraction method should be rapid. That means we should be able to extract as much samples as quickly as possible. The throughput should be, we call the term throughput. The throughput should be high, and the extraction method should consume very low amount of solvent. Solvents are extremely costly. Whatever the solvent which we use for our pesticide residue analysis, that solvent should be a HPLC grade, chromatographic grade. So that should be extremely costly. It should be extremely pure. So the quantity of pesticide solvent used should be extremely low. That is one thing. And it should have a recovery of 70 to 120 percentage. I will explain what is recovery. Recovery means if we add, we carry out some recovery experiments for every pesticide residue analysis. Recovery experiments means we take a sample without any pesticide spray, say an organic sample, say tomato, and we will add a known quantity of pesticide into it. We will add a known quantity of pesticide into the sample, say 1 ppm of pesticide I have added to the sample, and we will extract the pesticide and check for the quantity recovered from extracted from the sample. If it gives exact 1 ppm, it's fine, but normally it doesn't happen so, because during the extraction process and the next step, that is the cleanup process, there is a chance of loss of pesticide. So usually it is less than 1 ppm, and the permissible level is, it can fall up to 0.7 ppm. So if we have added 1 ppm to the sample, we should detect a minimum of 0.7 ppm. We should detect a minimum of 0.7 ppm. And here comes the next thing, we can also detect, the range is, we can detect 1.2 ppm also. That is also permissible. The here it's a bit it may be a bit confusing for you. You added only 1 ppm of pesticide and you understood, yes, it is up to 0.7 ppm. Yes, there can be loss of 0.3 ppm, and minimum we should detect 0.7 ppm. And how come we detect 1.2 ppm, that is 120 percentage? Here the thing is that, have you ever seen a chromatogram? Yes or no? Chances are very less. Yes or no? Chromatogram? No. We will discuss about chromatogram tomorrow. Okay. So what will happen is, the instrument which we use to detect pesticide residues, it can be GC, it can be GCMS-MS, or it can be HPLC or LCMS-MS, whatever be the instrument which we use, that we detect it based on the molecular weight, or sometimes the time at which the pesticide comes out of the instrument. We call it a retention time. So we normally, when we conduct an experiment, what we do is we inject the sample in the instrument, and for each pesticide, first we will inject the pure pesticide, so it won't contain any contamination. So pure pesticide is injected, so the pesticide will come out at a particular point of time, say 8th minute. So we have it will be like a graph like this. That graph, they will have a peak at 8th minute, and we say that that peak at 8th minute is pesticide, because it is a pure pesticide standard. It won't contain anything. So at the 8th minute, we say we have a pesticide, and then we inject the sample. That means a vegetable or a fruit containing pesticide. And whatever the thing if we the thing coming out at 8th minute, we consider it as the pesticide. So what will happen is that at 8th minute, there is a chance that along with the pesticide, some compound from the commodity also may come out. along with the pesticide at the same time. Say tomato, if you say we took the example as tomato. Tomato has lycopene, carotenoids, all other phytochemicals. These phytochemicals also can come out at the same time as that of the pesticide. So what will happen is that at eight time we have a exaggerated peak, the peak of the pesticide along with the peak of the phytochemical from the commodity. So instead of 1 ppm, we can have a phytochemical which is contributing to that particular peak, and that may lead to an exaggerated peak that will be lead to the figures such as 130%, 130% recovery as 130%. Are you sure about recovery 70 to 120 percentage? Yes. Okay. So that is recovery percentage 70 to 120, and the extraction method, we should the criteria should be extraction method should be rapid. We should employ very low amount of solvent, and it should be lead to good recovery, and it should be robust. Robust means if that method is employed in another lab, it should also give the same results. So that does the mean robust. So I told you we are using solvents for extraction. So we have a certain prescribed certain characteristics for an ideal solvent for extraction. The characteristics include the solvent should have high solubility for the extracting analyte. That means the solvent should have high solubility for the target pesticide. That means the pesticide should dissolve easily in that solvent. And the next point is that it should have very less solubility for interfering substances. That means I told you, along with the pesticide, we took the example of tomato. Along with the pesticide, from tomato phytochemicals, say lycopene also can be extracted with the same solvent. But the solubility of lycopene and other phytochemicals present in the sample should be as low as possible, and it should have high solubility for the pesticide. That means the solvent should be specific for the pesticide. That is one two characteristics of solvent. And the next thing is the solvent should not react with the pesticide. That you can understand. If it reacts with the pesticide, then pesticide will degrade. So it should not react with the pesticide. It should only dissolve in the solvent. Pesticide should only dissolve in the solvent. And the solvent should have low boiling point, because at one step we have to evaporate the solvent. Rahul might be knowing about rotavapor and all, evaporating solvent for various purpose and all. So at one point of pesticide residue analysis, we have to evaporate the solvent. And if the solvent is having extremely high boiling point, say methanol, ethanol, etc., it has a boiling point of 100 degree. So that means we have to boil the solvent up to 100 degree. At 100 degree, there is a chance of pesticide degradation of pesticide. So we use solvents such as ethyl acetate and all, which have extremely low boiling point, 50 degrees, 60 degree, etc. So at that time, at that temperature, the pesticide won't degrade, and it should be economical. That means the cost of the solvent should be low, and it should be compatible with the analytical method. I will discuss what this in the upcoming slides, how it is compatible and all. So the ideal solvent should be highly soluble for the pesticide, less soluble for the interfering substances. It should not react with the pesticide. It should have low boiling point, economical, and compatible with analytical method. This I will describe later. And the common solvents used are, the most common solvent employed in pesticide residue analysis nowadays is acetonitrate. Then here hexane is used, acetone, dichloromethane, ethyl acetate, ether, etc. are also used, but now most common one is acetonitrate. And there are several extraction techniques employed for extracting pesticide. Though there are several extraction techniques employed for extracting pesticide, nowadays the most common extraction method used is Quisher's method that we will describe later. But we will slowly discuss about different extraction method because certain commodities require a particular method of extraction. So the first method of extraction is tumbling. Tumbling is pretty simple. We will immerse the sample. The crushed sample will take. I told you the first step is crushing the sample in the blender. The crushed sample is taken in a solvent for 12 hours, and during occasionally we will turn the container. We will just invert the container. So this is called as tumbling. We'll take the sample in a solvent and occasionally we will turn the container. So by that we will be able to extract the dislodgeable residues. We won't be able to extract bound residues and all, but we will be able to extract dislodgeable residues because this tumbling method will help us to understand the risk of exposure to farm laborers, because farm laborers are the one which are exposed to dislodgeable residues. And the next method is shaking method. Shaking, you might have seen laboratory shakers. And here what we will do, we will take the sample, we will add the solvent and keep that container containing sample and the solvent in shakers for 20 to 30 minutes. So it will be mixed, the solvent will be mixed thoroughly with the sample and the pesticide will be extracted into the solvent. So the sample, so what we will do is, say we took 10 gram of sample, we added 50 ml of solvent, shaken it for 30 minutes in a shaker. Then we will collect the supernatant alone, that is the solvent alone, and to the remaining sample we will add again 50 ml. So that means like that we repeat it 2 to 3 times so that maximum pesticide is extracted. Then the third thing is blending using blenders. That means in a blender we can add what we have a blender called as homogenizer. I think I have a picture of it. Can you see it over here? Here. Here we have a small instrument here, this part. Here what we will do is uh, we will take the sample and solvent in a centrifuge tube, and the centrifuge tube containing the sample as well as the solvent is kept in a homogenizer, and this homogenizer will rotate at extremely high speed up to say 15,000 rpm. So that is called as blending. So that means the solvent will be blended thoroughly with the sample. So that is use of blenders. Then oxalate extraction, liquid extraction, solid phase extraction and all I will discuss with pictures. Liquid extraction, this is the method adopted for extracting pesticide residues from water. The adopted and the accepted practice for extracting pesticide from drinking water is liquid extraction. Here what we will take a glassware called as um separatory funnel. What you see it over here is this glassware. This glassware is called as this separatory funnel. This separatory funnel, what we will do is we will take water and we will take a solvent which is immiscible in water. That means water as well as solvent forms two separate layers. So here, say this is the solvent and this is water. So say consider solvent is heavier than water. We usually for extraction of residues from water we use a solvent called as dichloromethane. Dichloromethane. This dichloromethane, because of the presence of two chlorine atoms, it is heavier than water. So dichloromethane will be at the bottom. If you take pour dichloromethane in and as water into a container, dichloromethane will be at the bottom and water will be at the top. So the dichloromethane is here. You have water over here, and if we mix it thoroughly, what will happen is that the pesticides will separate out into dichloromethane, because the pesticides are extremely soluble in the solvent dichloromethane, and pesticides will separate out into dichloromethane from water, and this dichloromethane can be separated. We use the separatory funnel for separation. I will show how it is done. See here, here the solvent again used is methylene dichloride, that is dichloromethane. We took a separatory funnel. We are adding, I don't know which they are adding, either water or dichloromethane, whatever it may be, they are adding water or dichloromethane to the separatory funnel, and they close the separatory funnel. Here you see the cork is closed, and the top also with glass top cork we will stop. Then we will slightly invert the separatory funnel. Once you slightly you see my video, not check the don't see the slides. We will slightly separate out the we invert the separatory funnel, and we will open that stopcock at the bottom. We will invert the separatory funnel. Just a minute, I will show you how to do it. Okay, can you see this separatory funnel now? Yes. So what we will do is I will add a bit of water into it. Okay. I have added a bit of water, then add solvent into it and close it. Okay. And invert it. While you are inverting it, hold this stopcock tightly, because once you are adding solvent into this separatory funnel, it is a closed system. Solvent will release lot of vapor. Solvent evaporate pretty quickly. So the entire thing will be filled with vapors of the solvent. So you have to hold it like that. You see it like this. You hold it like this, without much shaking, you invert it and open this stopcock. You didn't heard, you might not have heard, but with water itself, once I really opened the stopcock, I heard the release of air from this tip. So once solvent is there, there will be huge pumping of air from it. But if you doesn't do it carefully, this container can burst. This container can burst and it can damage. So if you release this carefully, then close it again, slightly mix it, again release it, the air, then close it, mix it, release the air. So do it several times. Do it several times. After releasing few 5 times, we will usually mix it like this. Then release it, then mix it, release it. So in this manner, we will do it continuously. And once you keep it in the stand, just like the stand you have seen in the PPT, immediately you should release the stopcock and keep it here, keep it on the table. Otherwise, what will happen is that if you keep the stopcock in, slowly air will fill in then and it will push it. So many times it happened in labs. So that's why practically whenever you are doing this separatory funnel, you should be extremely careful. But this is the method which we are using for pesticide residue analysis. So are you clear? And one thing, so you have mixed it and you've kept it for separation. So what will happen? You will have one layer of water. If you are adding solvent, it is immiscible in water. So that means it won't mix with water. So I told you we use dichloromethane. Dichloromethane is heavier. So dichloromethane will, if you keep it idle for 2 to 3 minutes, what will happen is that we will have two layers. The bottom layer will be dichloromethane and top layer will be water. So what we'll do is we will slightly open this thing, this top cork, and we will separate out only the dichloromethane layer. And once the dichloromethane layer is completely removed from the separatory funnel, we will immediately stop it. We won't allow the water to come out of the separatory funnel. Then we will add second time dichloromethane. We will again extract. We will then remove the solvent. Then third time. So we will repeat it 3 times for a single sample so that the entire pesticide residues are extracted from the water sample. Are you clear now? How liquid extraction is done? Okay. So then we can go back to the slides. So here that person is mixing, then you can see he is releasing that air. Then we will keep it. You see, once they are keeping it, they are removing the stopcock. Otherwise, this stopcock will bump. And if you examine it carefully, you can see two layers. We will remove the solvent layer and the water layer. Again, we will add solvent. We will repeat it thrice. That is liquid extraction. So the steps we have discussed: liquid sample and solvent added added to separatory funnel. Close the funnel and shake it vigorously. Invert the funnel and release the pressure. One thing in the second step: close the funnel and shake vigorously. For the first time, you should not shake vigorously. Close the funnel, invert it, immediately release the air, then close the stopcock, then slightly shake it, release the air. You can increase the shaking strength each and every time, but in the first time don't shake vigorously. Then keep the funnel in stand to separate out the layers, and once the layers are separated, open the bottom tab to collect the layers separately. So this is liquid extraction. Here, one thing is that still this is the method used for extraction of pesticides from water, drinking water. And this method for extraction of residues, it takes more than 1 hour for extraction, and it takes huge amount of solvent also. So this is a cumbersome procedure, consumes a lot of pesticide solvent. And the next one is solid phase extraction. Solid phase extraction for certain kind of pesticide residues, solid phase extraction is also used. Here, what we will do is, here one major problem with the liquid extraction is that there can be chances of emulsion formation, because if the thing is not properly dissolved in water, it can form emulsion, oil in water emulsion or water in oil emulsion, like that. So that is a kind of problem with liquid extraction. So solid phase extraction removes it. Here, what we will do is, here it is just similar to our syringes. നമ്മൾ syringe കണ്ടിട്ടില്ലേ, without any needle, that plastic syringes which we use in hospitals. So this we call it as cartridges, and this cartridges will be filled with, it will be pre-filled with stationary phase material, solid material. We can purchase this plastic material, it will be looking similar to syringes, and it will be filled with certain adsorbent material, we call it as stationary phase. And we will add sample to it, say the vegetable is added to the top of it, and this is the stationary phase or adsorbent phase. As the name indicate, it has the stationary phase, has the ability to adsorb material. And in the next step, what we will do is we will add solvent. So once we add solvent, what will happen is that the sample, the components in the sample, the phytochemicals in the sample, as well as the pesticide, will dissolve in the solvent, and it will start moving down. But the speed of movement differs for each and every chemical. If a chemical is extremely soluble in the solvent which we are using, and it doesn't have any affinity for the stationary phase, I will repeat, if a chemical in the sample is extremely soluble in the solvent and it doesn't have any affinity towards the adsorbent material in the stationary phase, it will come out quickly because it is soluble in the extremely soluble in the solvent, and it doesn't have any affinity for the stationary phase. It comes out along with the solvent as first. But if the chemical is having very high affinity towards the stationary phase material, so what will happen is, it's an adsorbent. I told you the stationary phase particle is an adsorbent. So the chemical, if it has very high affinity towards the stationary phase, it will get adsorbed onto the particles of stationary phase, and the solvent will be the solvent won't be able to extract the pesticide easily, and the chemical which is having very high affinity towards the stationary phase will be the last one to come out of the cartridge. So in this manner we can separate out pesticide from the plant phytochemicals, the any sample material. Do you understood what I told? Have you gone through that column chromatography and all which materials I have given you for laboratory techniques course? In that I have explained this column chromatography. This is nothing but a kind of column chromatography. Are you clear about it? Solid phase extraction. Yes. Okay. Because this is pretty simple, because certain chemicals has very high affinity for the solvent, certain has very low affinity for the solvent, and certain chemicals have very high affinity for stationary phase, some have very low affinity for the stationary phase. So those which have very low affinity for the stationary phase, it comes fast. Those have high affinity for the stationary phase, it will be adsorbed onto it. So this every material have different affinity, so we explore the affinity or the absorption to the stationary phase. So the sample is passed through a cartridge or a packed column, we usually call it as a packed column, filled with a solid adsorbent. I told you it is an adsorbent, on the surface of which the analytes are chemicals, are adsorbed while the other sample components pass through the bed. The common stationary phase which we use is alumina, fluorosil. We few more we use silica gel, etc. We use. Yeah, it's a very simple process. It's a very small cartridge. Earlier, we used to extract it with very 100 centimeter, 100 ml columns. So earlier we used to use with that. Nowadays, smaller cartridges are used. So we use only very small volume of solvent, and it avoids the formation of emulsion. I told you in liquid extraction, emulsion formation. As we mix two immiscible solvents, the chances of emulsion formation is high, but here it's not so, so there is no emulsion formation here. So this is another typical thing. The first step is conditioning. Conditioning means nothing but adding just the solvent alone without before adding the sample, then add the sample and then add the solvent. You can see the sample contains different components. See, you can see triangles, squares, circles with different colors, and based on the affinity to the adsorbent, it will move out according to the affinity of to the adsorbent and affinity solubility in the solvent. We continue to add the solvent. First it came the green square, then came the triangle, then came the red circles, and last came the yellow circles. Now, one thing you may ask, how in a solvent you can identify whether solvent is present, whether the pesticide has come out or not. We have ways to do it. We use a methodology called as TLC. So in TLC we can know whether the solvent is coming or whether the chemical has come or not. There are methods for doing that. So this is how a cartridge looks like. That's why I told you it looks like a syringe. And this is nothing but a Soxhlet extraction. Here in Soxhlet, have you ever seen a Soxhlet extraction in your UG? Yes or no? Soxhlet extraction? No. Okay, Soxhlet extraction here, this is the setup of Soxhlet extraction. You can see here is a heating mantle, and we have a round bottom flask over here. And this glassware, this structure is called as Soxhlet apparatus, and at the top we have a condenser. We have a condenser. So what we will do is, inside this Soxhlet extraction apparatus, here you can see it over here. This is the round bottom flask, this is a Soxhlet extraction unit, and this is the condenser. So inside this Soxhlet extraction unit, we will place the sample. We will place the sample in a paper thimble. We will You see my face. We will prepare a thimble like this, or we will prepare it like this. We will staple it over here, and we will place the sample it over here. Don't think that there is it will be open over here. We will place it as if it won't go out. We will place the sample it over here, and we will keep this paper thimble inside the oxalate extractor. So once this paper thimble will be there in the extractor, and in the round bottom flask we will take the solvent and we'll start boiling the solvent. This solvent will evaporate, it will move upward, and here it is sealed over here, there is no opening over here. The evaporated solvent will move through this part, this arm, and once it reaches the condenser, we will be passing water through this condenser. This vapors of the solvent condenses and it condenses, and the solvent will again liquefy and it will falls over this sample kept in the paper thimble, and the solvent will fill inside this, and once it reaches this level it siphons out, automatically siphons out. We don't do anything, siphons out, and this cycle continues. The advantage is that we are using the solvent again and again for extraction. The quantity of solvent used remains the constant, and we will be repeating the cycle for 2 hours, 3 hours, like that. So what is that? With 2 hours and 3 hours, so many cycles will continue, and during this time all the residues from this sample kept in the paper thimble will be extracted. Are you clear with respect to oxalate extraction? We have all those things. I have arranged all those things in the lab, but what to do? Okay. Then the sample is placed in the extractor and paper thimble. Reflex. We call this is reflexing here. This continuous siphoning and filling of this oxalate extraction. This is called as reflexing. Reflexing, the condensed solvent will be filled in the extractor. Once the extractor is almost full, the solvent siphons automatically into the round bottom flask. This process is repeated uh, again and again. As I told you, the solvent requirement is low. This is mainly used for extraction of pesticides from spices and cereals. Though we have certain other quicker methods also, but for certain spices and all, this is the method which we use. So now we have completed oxalate extraction techniques. Now the next step is cleanup. So even though I told you we should use a solvent which have least solubility to the co-extractives, some co-extractives will come up in our during our extraction procedure. We won't get an extract wherein we have only a pesticide. We will have phytochemicals also extracted along with pesticide. And these phytochemicals extracted along with the pesticide will interfere with our analysis. So these phytochemicals extracted along with the pesticides is called as co-extractives. You can see it over here. It is called as co-extractives. You can see co-extractives or impurities. So we have to remove co-extractives. This co-extractives include moisture, chlorophyll, fatty acids, oils, etc. So moisture and all, it is extremely bad for the instrument. So we have to remove moisture, we have to remove chlorophyll, fats, etc. And it, as I told you, the solvent should have high solubility for the pesticide and low solubility for co-extractives. And we have several techniques for cleanup. This include liquid-liquid partitioning, I told you. Then column chromatography. The column chromatography and solid phase extraction is almost the same. In column chromatography, we use long burettes, 100 ml burettes we use instead of the small cartridges which we use in solid phase extraction. Otherwise, theoretically, both column chromatography and solid phase extraction is the same. And next step is chemical cleanup. Chemical cleanup, this is mainly used for oil seeds and all, where oils and fats will be extracted along with the solvent. And here we use sulfuric acid and all to remove lipids by saponifying with potassium hydroxide. So this is a method of saponification. And sometimes it will help to precipitate and remove chlorophyll and other pigments. Then there is another method, cleanup method called as gel permeation or size exclusion chromatography. This is nothing but separation of molecules based on molecular weight. Uh, you might have studied in molecular biology, biotechnology with respect to gel, how we separate out proteins in a gel. What is the basis of separation of protein in a gel analysis? SDS page. We use polyacrylamide gel electrophoresis. In gel electrophoresis, how proteins are separated? Do you remember? Or you haven't studied, or you don't remember? Anyone? Don't remember. It's based on size. You might be remembering a protein ladder of definite molecular weight, and you run the sample along with the ladder. So based on the position of the sample and the ladder, we compare it with, and we can know the molecular weight of the thing. So it's based on size, molecular weight. So this is almost similar to that. Based on size, we can separate it. This SDS page is also a separatory technique based on the size. So this is separation based on size. So up to this, what I have told is was the major extraction and cleanup technique adapted in pesticide residue analysis may say till 2005. In 2003, a method was invented by a person called as Anastasidus, and that method is called as Quescher's method. Once Quescher's method was invented, it revolutionized pesticide residue analysis. It became extremely quick. It became extremely easy, cheap, effective, and safe method compared to this. All these methods, though still we employ some of these methods for residue analysis, Quescher's method is the one which is employed for say 70 to 80 percentage of the samples all over the world. Though Quescher's method, it's every lab modifies the Quescher's method so, according to our own requirements. So it's called as modified Quescher's method, but the basic principles remains the same. It was developed by Anastasidus in 2003 and modified by several each and every lab. We use a method which is a modified version of Quescher's method. So this you should write questions like this. You should be not be capitalized ECHES. So it should write it like this. It represents quick, easy, cheap, effective, rugged, and safe. So quick, easy, cheap, effective, rugged, and safe. Quick means the extraction and cleanup can be completed pretty fast. Here we can complete extraction and cleanup say within 20 to 30 minutes for a sample. It's pretty easy. Very less number of steps are involved. Cheap, that means we employ very low quantity of solvents. That means we hardly employ 10 ml of solvent for Quescher's method. And it is extremely effective because it has very good recovery. And rugged means it can detect large number of pesticides. With a simple Quescher's method, certain labs have standardized methodologies for extracting about 300 pesticides from a single sample. That means they will that doesn't mean that 300 pesticides are sprayed on a sample. What they will do is they will take a sample, add 300 non pesticides into it. They will extract it using the Quescher's method, and we will check whether what is the recovery. And this method, Quescher's method, has the ability to extract this wide range of pesticides, and it is safe. This is a typical flowchart of Quescher's method. Actually, we do it in a practical, so that's why I simply give this. I will explain how it is done. We will take sample, the sample size, as you all know, as FSSI prescribed, we should take 2 kg of sample. We will crush it. The crushed sample is taken in a container. We will label it, and we will take 10 gram of sample into a 50 ml centrifuge tube. In a bigger centrifuge tube, we will take 10 gram of the sample in 50 ml centrifuge tube, and into the centrifuge tube we will add 10 ml of ethyl acetate. In original Kesher's method, we will use it is acetonitrile is the solvent used, but here we have modified it. We add 10 ml of ethyl acetate and 9 gram of anhydrous sodium sulfate plus 1 gram of sodium chloride. To 10 ml of ethyl acetate, we took 10 gram of sample, add 10 ml of ethyl acetate, 9 gram anhydrous sodium sulfate and 1 gram of sodium chloride. Then homogenize the sample. This is the homogenizer I told. We mix it thoroughly, homogenize it thoroughly in a homogenizer at 13 to 14,000 rpm for 3 minutes. So the sample will be thoroughly mixed with the solvent, and this centrifuge tube will be then transferred to a centrifuge, refrigerated centrifuge, and we centrifuge it at 3000 rpm for 5 minutes at 10 degrees Celsius. So we centrifuge it at 3000 rpm. So, and once the centrifugation is over, we will get a supernatant, and we will separate out the supernatant. We will pipette out the supernatant. Usually we will get, if we take 10 ml of the solvent, we will get around 6 to 8 ml of extract, and this supernatant will be transferred to 15 ml centrifuge tube. Here we will take smaller centrifuge tube. 6 to 8 ml of extract will be transferred to 15 ml centrifuge tube, and into that centrifuge tube we will add 50 milligram PSA. PSA means primary secondary amine, and 150 milligram of magnesium sulfate per ml of supernatant. That means if you are taking 6 ml of supernatant, we will be adding 300 gram of primary secondary amine and 300 milligram of primary secondary amine and 900 milligram of magnesium sulfate into it. Again, we will mix it thoroughly. We will centrifuge it at 5000 rpm for 5 minutes, and here we have extracted with ethyl acetate. And ethyl acetate is a solvent which can be injected in an instrument called as gas chromatograph or gas chromatograph. So here in gas chromatograph we can use two kinds, mainly two solvents. One is hexane and another one is ethyl acetate. Since we have used ethyl acetate over here, what we will do is once this centrifugation is complete, we will get a supernatant like this. This supernatant, we will take it in a syringe. We will filter it through a syringe filter. We have a particular kind of filter called a syringe filter. We will take 2 ml of this supernatant, filter it through a 0.2 micron PTFE, polytetrafluoroethylene membrane filter, and we will keep it for analysis. But the major problem with ethyl acetate is that ethyl acetate cannot be used for LC analysis, HPLC or LC-MS-MS. That's why I told you I will explain about the solvent should be amenable for a particular kind of analysis. Here our lab mainly uses GC and GC-MS-MS. So here we use ethyl acetate. If we are using LC or LC-MS-MS, we can go for acetonitrile. Acetonitrile is a solvent which can be used in liquid chromatography, HPLC or LC-MS-MS. But hexane or ethyl acetate cannot be used. So what we will do is, here we have used ethyl acetate. What we will do is we will take the supernatant, 2 ml of supernatant. We will transfer it into glass vials and keep it in this instrument. This is called as nitrogen evaporator. And what this instrument does is it will evaporate all the solvent. We have 2 ml of ethyl acetate in the glass vial or kept it over here. It will evaporate all the ethyl acetate, and what we will do is once the complete solvent is evaporated, we will add 2 ml of acetonitrile into it, or any other solvent which can be used in liquid chromatography. Here we have used methanol and acetic acid and HPLC water. Methanol, acetic acid and HPLC water can be used in liquid chromatography, so we can use it. So we will reconstitute it once the entire ethyl acetate is evaporated. We will make up that glass vial with 2 ml of the solvent which we are using it in liquid chromatography, and then we will filter it again in membrane filter, and you go for chromatographic analysis. Are you clear about the steps in Quashes method? Many of you are leaving in between. Yes or no? Yes. Okay. Then one more thing. I told you we will be adding sodium sulfate, sodium chloride, magnesium sulfate, primary, secondary amine, and there are certain role for each and every reagent. Primary, secondary amine (PSA) is nothing but I will just one thing. Up to this step, the first centrifugation, this is the extraction step, and the subsequent steps are cleanup stage. In Kesher's method, extraction and cleanup steps are combined. Up to this first centrifugation, this is extraction, and the next steps, adding primary, secondary amine, magnesium sulfate, and all these are cleanup steps. So primary, secondary amine is nothing but an adsorbent, and this is added as a cleanup agent. And this primary, secondary amine will remove all the fatty acids, organic acids, sugars, and all from the sample. So this is a cleanup method. This cleanup method is called as dispersive solid phase extraction. Solid phase extraction, I told you, SP, solid phase extraction cartridges. Here we are adding the sample and we are extracting the pesticide alone. In dispersive solid phase extraction, this is an adsorbent. Primary, secondary amine is an adsorbent, and what we are doing is primary, secondary amine is added into that. We are dispersed in that material. So hence it is called as dispersive solid phase extraction. Next thing is we added is magnesium sulfate, anhydrous magnesium sulfate. This is to remove water, remove moisture, water. And another thing is it facilitates solvent partitioning. Solvent partitioning means uh, once we add any salt into a system, we call it a salting out phenomenon. We call it a salting out. നമ്മൾ ഏതാണ്ട് പുകച്ച് കുറച്ച് അടിക്കുക, smoking out, the similar to it. What will happen is that if you add more and more salt into a system, the salt will try to attach on to the substrate. Here they say commodity, any fruit or vegetable, say tomato. The salt will try to attach on to the tomato, and this tomato will be having lot of pesticide molecules also. So once the salt is trying to attach onto the plant material, it will remove all the pesticides from the site of attachment. So it is called a salting out. So it will improve the recovery of the pesticide from the sample. And in some analysis, we use acetic acid and sodium acetate. Here, what methodology I have explained, we are not using acetic acid and sodium acetate. It is used to certain methodology, use it to adjust the pH. And sodium acetonitrile is the solvent preferred in Kesher's method because this is the one which has the ability to extract the maximum number of pesticides with least co-extractives, and it is amenable for LC. GC, it's not that good. That's why we don't normally use acetonitrile for GC. And it is from acetonitrile, it is easy to remove water. Methanol also can be used, but methanol, the problem is removal of water is extremely difficult. And sodium chloride is added to reduce the amount of polar interference. That means sodium chloride will remove the polar material from the sample. Those material which are, sodium chloride is extremely polar, so it will remove all the polar material from the sample. Then anhydrous sodium sulfate, it is also used to remove water. So each and every chemical which we are adding for Kesher's method has its own purpose. Primary, secondary, I mean, it's cleanup method. Magnesium sulfate and sodium sulfate, it will remove water. Acetonitrile, it is one of the best solvent. Sodium chloride to reduce the polar interferences. And sodium sulfate and magnesium sulfate, it improves the solvent partitioning, separation of pesticides into solvent. So this is with respect to the pesticide residue analysis steps. And only I think I will complete it in the next two classes. It is analysis and interpretation of data. Analysis will study a bit about instrumentation. I don't know whether I will be able to complete in two lectures, maybe three. Are you clear with this? What I taught you today? How to remove chlorophyll? Chlorophyll, we can't remove it completely. Though we can reduce the amount of chlorophyll, primary, secondary amine is the one which removes chlorophyll. One more thing is that sometimes we use another adsorbent in Kesher's method called as GCB, graphitized carbon black. Graphitized carbon black, GCB. GCB is the one which will remove more of chlorophyll, but GCB we don't employ it much over here. Using GCB is good because it will reduce the interference from many other but GCB, the thing is, you can understand carbon is extremely good adsorbent, and carbon can absorb pesticides also. So the recovery may reduce if we use GCB. That's why we doesn't use GCB over here. So different methodology, if we have some interferences from some particular material, we can add particular kind of material into this different steps, and we can avoid that. That is the flexibility of it. That's why we call it as a modified Kesher's method, because we can modify it according to our wish. Any clarification needed? Shikha is not seen. Okay, then I think I will take class tomorrow also. Okay, fine. Thank you.